Hello, it is February 17th, and today we'll be doing part 5 of homework 2. We're going to be looking at the Maxwell construction and how we can use that to plot the two-phase envelope. So first of all, let's look at the Maxwell construction. So if you see here, we have an isotherm, and with the pressure line, the horizontal pressure line, and we have two shaded regions of the isotherm above and below that pressure line. Basically, what the Maxwell construction is saying is if we take the integral of this line at these points and find the area of these two green halves, set them equal to each other, they should equal 0, and then we can use that information to solve for the two-phase envelope. Now, what is a two-phase envelope? It is the solid black line that we see on the P versus V, pressure versus specific volume diagram that separates the two phases, the liquid and the gas phase, and then it comes to the point, and then it comes to a point at the critical point. That is the two-phase envelope, that solid line that separates those two phases. Okay, so like I said, we need to integrate this line and solve for the area of these two regions. We already found the roots of this line. We have a root here, and a root here. That was our v values, or z that we transformed into v values in the last part. So now let's continue that. So now we need to integrate at those roots. So one way we can integrate is using quadrature process, which is basically an integral way of determining area, which is exactly what we need. And we can actually do quadrature in Python. All we have to do is import from SciPy, integrate, import quadrature. So let's do that. Def no, let's not do integrate. Let's do areas because we're solving for areas. So let's do areas quad, and that is of course dependent on the pressure, but it's also dependent on the temperature, as we will see. So temperature and pressure. So now let's define the integrand. What are we taking the integral of? So the integrand is v, right? Because we solve for v up here. So the integrand is v. Right? The integrand is v, yes. So, well, actually, we do need to pull in v. So v1, v2, and v3 are equal to cubic v, and that is p. Alright, let's just check everything so far. If it wants to run, yeah, we'll get there. I did not run everything first. Let's do that. Okay, now let's return something. We need to return the values that we calculated. So this needs to be down here. Perfect. Okay, now in order to find these areas, we need to subtract this point from this point and this point from this point. So let's do that. So we need to, on the outer one, we need to return these quad, that we have the integrand of v1 integrand v1 v2, and that has, we just want the first point of that array, and then the other one quad integrand of v2 v3, and that is 0 as well. Right, correct. Perfect. Where to find it here, guys? I think this needs to be on this end, actually. There we go. Okay, now we have the code to solve for the integral and find the area of those two spots. Now we need to basically add them together to see if they equal 0. So let's do that. So that is area, and then so basically we're taking the difference of them, seeing the difference. So area difference, and that is obviously dependent on pressure and temperature again, but we see in the Maxwell construction that pressure is a vector, so we're going to make that pressure a vector. So we're just going to say P is equal to the vector, and just the first in that vector, so just 0. So then we need to specify the left side, yes. No, the left side and the right side is equal to the what we did just above, areas quad of P times T, and then we need to return the addition of those. Why can't I spell? Scroll this up so my head's not in the way. There we go. We're gonna make this areas. Make that areas. All right, now let's just check this. Let's do 9800 and 400. Ooh, does not like that. Need periods. Is that too big? Forget it. Okay. Now that we have that code, which is basically just adding the two together, we need to find values for that, for those areas. That we need to plug in the right variables to make sure that those are equal to 0, the right temperatures and the right pressure, so that these two areas can equal 0, so we get the correct two-phase envelope. Now we could do that by just guessing and checking, but it would be much better if we actually wrote code so that Python can give us that correct value. So let's do that. Okay, so what I just did there, so like I said, we need to create a way for this code to decide the correct variables, so it chooses the ones that make these areas equal to 0. Well, when they add up, they equal 0 because one is negative and one is positive. So how we did that was we made a range of temperature values to plug into our root equation, and then our temperature variable, we put in a guess, but we have it as an array so that it can update every time we run the system through. We also created lists for the vapor pressure, the volume of the liquid, and the volume of the gas to update every time it goes through as well, so they can just keep running so that it can keep figuring it out. And then when this spits out, it spits it out as an array, so we just want the x values, but we only need the first one, or just the one. So that's why that is there. But it does not like that. So let's figure out why it does not like that. Alright, this is supposed to be just add root, I think. Let's run this. Oh, this is supposed to be pVap. That's why? Okay. Pressure of the vapor. Alright, now we want to assign the information that this is giving to a new list that we can put on a graph. So we can graph the envelope on top of our already made isotherm graph. So let's do pplot, and that is equal to pvap list plus pvap list. Just basically doing both, but one is on the opposite side, so it creates the whole envelope. And then v list equals v liquid underscore list plus v gas underscore list. Now this one is the exact same, similar to the vapor pressure, but since the vapor pressure is the same on both sides, we don't have to. It's the same, but on both here, but since the the volume of the liquid, or since it's a liquid on one side and the gas on the other side, that's why we have gas on the side. All right, make sure that works. Good. Okay, now basically we need to make a graph. So let's go pull in this exact same graph we had. Control V. Let's name this 2 just so we don't mix it up. Alright. Good, good, good. So now let's make another graph. We're going to do fig 2 and scatter our x. Remember, we want the x to be the v. So we have, let's get rid of this. We have v list. V list. We want our y to be p list, p plot. Hold on. We want this to be plot. Okay. We want our mode to be lines. and we want the color of this to be white so we can see it easier. So line color equals white. Alright. There we are. There is our two-phase envelope. So let me reiterate what this does. This separates the phases on the pressure versus volume chart that we plotted our isotherms on. This top point here, this where the slope is 0, is the critical point, and on the left side is the gas phase, and on the right side is the left side is the liquid phase, and the right side is the gaseous phase. And there's really no real anything that in the world that lives in this middle region. So that is what this solid line represents. Most things fall on this line, or everything falls on this line. And like I said, the slope when the slope is 0 at the top, that is the critical point. And this chart is again for water. So thank you very much.